Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class, and I'm putting it online in case it would be helpful to others as well. In the description of this video, there is a printable set of guided notes that you can use to follow along with the problems as I go over them. Usually I start my videos, I get made fun of for this, I start my videos by saying, this is one of my favorite sections. And for the first time ever, I'm going to tell you this is not one of my favorite sections. I don't know why. Well, I actually do know why. I can't get into volumes of solids of revolution. It is because it is always at the end of the year. We are always rushed at that point, and I just never have the time to put into it. So this year, I tried to change that. I tried to really dive into it a little bit more and get excited about it. It worked slightly, but we're still sort of pressed for time this year. So again, it's just sort of like, oh, okay, let's just get this done. Okay, with that being said, that's just my opinion. You might find that what we're about to do is really cool, because it is. Again, it's just usually the timing of it is not great. Okay, so what we're going to talk about in this section, we are just going to touch on some simple examples of what are called disk method and washer method, which are methods that you will see for using integrals to find volumes of three-dimensional shapes like this. Okay, and what you're going to see is we're going to take a curve, the curve of a function, and we are going to revolve it about an axis. I think most of these examples, if not all of them, are revolving around the x-axis. Okay, but then when we do practice, you'll see a revolving around the y-axis and other lines as well. Okay, but for now, let's just do baby steps, and that will be taking a curve, revolving it around the x-axis, seeing the resulting solid, and then talking about how to use integrals to find the volume. At the beginning of your notes, you have a picture of what is called a lathe, okay? And if you don't know what a lathe is, there's a little definition for you here. It's a machine for use in working wood, metal, etc. that holds the material and rotates it about a horizontal axis against a tool that shapes it. And I just thought that was kind of a cool way to start, to think about, what you're going to be doing with curves and on the coordinate plane. You're going to be rotating those curves about the x-axis for these examples, and we're going to talk about the shape that results from that and how to find the volume of the shape. Okay, so let's start with a simple example. Consider the area bounded by the function y equals 3x and the x-axis on the interval from 0 to 1. So let's take a moment and draw that. Okay, so we are looking at y equals 3x. I think at this point I would be good at drawing straight lines on here. Y equals 3x on the interval from 0 to 1, so that's just like, let's do 0, 0, and 1, 3. Maybe we should spread that out a little bit more. 1, 3. Okay, so we're talking about this area. And the question is, if the area is rotated 360 degrees about the x-axis, what is the resulting shape? And then a follow-up question, how can we find the volume of this shape? So usually I ask my students to think about this. Okay, we have a triangular region and we are revolving it. So, we're going to be the lathe, and we're going to, take this shape and revolve it about the x-axis. And what kind of three-dimensional figure would come out of that? Okay, are you thinking a cone? That's what my students usually come up with on their own pretty easily. And here's a better picture than I can draw. Okay, take a look at this. This is cool. Look at that. All right, so here's a little bit of a better graph, except I don't like where the numbers are. This right here, note, is the x-axis. Okay, so we're talking about the area of this region, triangular region, revolving about the x-axis, and what we get out of that is a cone. Okay, so again, how could we find the volume of this shape? That's what we want to talk about. Well, there is a volume formula for a cone, right? It's a third of the volume formula for a cylinder. So it's 1/3 pi r squared h. But we're in calculus, and I hope you know at this point that just one formula for one shape isn't going to do us much good, right? What happens when I change the function from a linear function to, I'm just showing you all sorts of good things coming up, huh? What happens when I change it to a curve like this, x cubed plus 1, and you get this sort of shape that kind of looks like a cone, but it's not, right? Because of this curving happening right here. What are we going to do at that point? So again, yeah, you could use 1/3 pi r squared h, and why don't we go ahead and do that so that we know the answer we should be getting when we're going to do it another way. Okay, so using 1/3 pi r squared h. Let me just double check. The radius, okay, is this length right here, which is 3. And the height is how far you're going along the x-axis. This is your height. The x-axis is going from the base all the way through to the vertex of the cone. And that's actually just 1 in this case, right? We were just going from 0 to 1. And, simplifying there, we get an answer of 3 pi. Okay, but again, when we move from a linear function to a curved function, we're going to have trouble if we're trying to focus on just using formulas of shapes that we know, like cones and cylinders and that kind of thing. Well, actually, we're still going to stick with a cylinder, but in a little bit of a different way. Okay, notice that what is marked here in yellow is sort of the outline of what would be a cross section, what we call a cross section of this solid. And I want you to think of a cross section as like, maybe you could think of it as like slicing a really thin piece out of this solid, pulling that out and looking at what shape you get from, from that slicing. Okay, in this case, it would be a circular base with a tiny bit of height. So we're going to say like a really short cylinder. Okay. And we could do that all throughout this interval. We could say, let's take a little tiny slice, a little tiny slice, a little tiny slice, and they would all be really short cylinders. And we could find the volume of all of those cylinders, add them all up, and that would give us a pretty good approximation of the volume of this shape, of this cone. Okay, we talked about this in my class way back at the beginning of our study of integrals with the wine barrel. There was Johannes Kepler looking at a wine barrel, trying to figure out how to approximate the volume of it. And the first thing that he did was say, let's use like manhole covers and stack them of different radii. And those are all short cylinders. And then let's change to something thinner. Okay, like paper discs. Okay, think of this cross section as one of those discs. Okay, so what we're going to do is we're going to say, let's find the volume of one of these cross sections, and then let's do that for the entire interval, add them all up, and we will do that as an integral. We'll make an infinite amount of them, and as we know, an infinite sum turns into an integral in calculus. Okay, so here is the, here is the formula that we're going to be using. Pi r squared, okay, there's an integral in there. I'll talk about that. And then there's a dx, which actually is important. Okay, where does all of this stuff come from? Pi r squared dx. What is all of that stuff? Well, let's think about a cylinder for a moment. The volume formula for a cylinder is pi r squared h. Or in other words, it is the area of the circular base. Oops. The area of the circular base, let me try that again, times the height. it's important to note that really this formula is coming from the area of the base times the height because, at some point we will talk about there being different types of shapes for the cross section, such as squares or triangles. And you can still apply the formula that you're using here for what is called a disk method. Okay, what we're talking about right now is called disk method. It's just you will not be using area of a circle times the height. You'll be using the area of some other shape. Okay, anyway, this is the volume formula for a cylinder. And, what you can think of it as in this form is different layers of the cross sections, pi r squared h, the dx is the h, all added up, an infinite amount of them added up, and that's why we have our integral symbol there, okay, over the interval that we are looking at. Okay, so again, pi r squared comes from the area of the circular cross section times the height. The dx is actually the height. It's an infinitesimally small height because remember, it's just like a slice out of the solid. Okay, and then there's an infinite amount of them, and that's why we have an integral there. All right, so why was there jelly beans? Well, I want to tell you that I actually apply this type of thinking to, party games where you might have a jar full of jelly beans and you have to guess how many jelly beans are in the jar. What I remember doing many times is sort of whispering to my niece or my daughter about, how many jelly beans are in the jar. And what I did to figure out the answer was I looked at one layer of jelly beans. Okay, I could turn the jar over and look at the bottom layer of jelly beans, count how many jelly beans were on the bottom layer, and then count how many layers up you need to go. Multiply those numbers. How many jelly beans are in one layer times how many layers are there? And you got your answer. Okay, it's usually a really good estimate. And people would say, why are you always so close? Well, it's because I know calculus. That's why. All right, so let's apply this formula to the cone example that we were working on back here. We know that the answer we should get is 3 pi. But how can we get that answer using the formula? The formula is v equals pi times the integral from a to b of capital R of x d squared. Sorry, I always forget the squared. I think that's another reason why I dislike this section is because I just always lose that part, dx. But when I start to talk about other cross sections, I don't lose sight of the fact that I need the area formula here, pi r squared. I don't know. I guess I do them too fast. Okay. How can we apply this formula to this example? Well, in this example, our interval, let's start with something simple, is from 0 to 1. So that would be the limits of integration on our integral. The r of x is going to be, if we look at this cross section, right here, this length, which is from the x-axis up until you hit the function. The function is y equals 3x. So this is y, right? All the way out here, it's 3, but it's any y. Or in terms of x, notice it says r of x, it is 3x. So we would want to change the r of x to the function in this example, 3x, and it is squared dx. Okay, pretty simple integral. We could clean it up. Maybe I should put this underneath. 3x squared can be simplified to 9x squared. And from here, we are just getting, we're taking pi times the antiderivative of 9x squared. What's that? Antiderivative of 9x squared. Add 1 to the power, that's x cubed, multiplied by the reciprocal of that. 9 times a third is 3. So 3x cubed, evaluated from 0 to 1. Okay, let's do plugging in the upper limit of integration minus plugging in the lower of limit integration. I think we could probably do that in our head. Plugging 1 in for x would give us 3. Plugging 0 in for x would just be 0. That gives us the answer that we knew we should have gotten. 3 pi, yay! Okay, so for this example, and actually this is going to be the case for all of the examples in the notes, the r of x that you see right here is going to be the function, okay? Because we are revolving around the x-axis, we can just look at it as the function. When we start to look at some other examples where we're revolving around different lines, we'll need to talk about how that r of x changes, but we're starting with simple things in this set of notes. Okay, so let's try a couple more where we have some other different types of functions. Example 1, find the volume if the area bounded by the curve y equals x cubed plus 1, the x-axis, and the limits x equals 0 and x equals 3 is rotated around the x-axis. I like this example because it shows you the resulting figure, which I think is nice to see. Whoops. The original graph, by the way, like if you would graph this for yourself, you are just going to see something like this over that interval. Okay, that's all you're going to see. But there are generators online that you could put this function into a volume of solid of revolution generator, and it will show you what the shape looks like in case you ever feel like you need to see that. Okay, in class, for those of you who are in my class, I'll show you that as we do practice. Okay, but again, what we're doing is we're taking this function's curve, which is just looks like this from 0 to 3, and we are turning it into this three-dimensional shape by revolving the curve about the x-axis. How do we find the volume of that shape? Well, the volume for disk method, okay, you can see that the cross section is circular, and so we are using what's called disk method here. Always starts with a pi, then an integral over the interval. This one is 0 to 3. Capital R is going to be the radius of the cross section, which again, in this case, is just going to be the function. So we're going to have capital R of x be x cubed plus 1 squared dx. And just to save some time, okay, if we were to do this by hand, we should probably expand. We definitely should expand x cubed plus 1 squared. And then go for an antiderivative. But I'm just going to, sort of skip all of that and tell you that the final answer here, okay, whether you're going to do it by hand or by a calculator, is 4,983 pi over 14. Okay, or that's approximately equal to 1,118.183. Pretty simple, right? Take a look at the U-try. Find the volume of the solid produced by rotating the curve y equals x squared plus 2 about the x-axis on the interval from 0 to 2. Okay, so for this one, you do not have a picture to go by. But anytime you are revolving or rotating a curve about an axis, you can assume that you are going to be using disk method. Okay, so the cross sections will be those circular cross sections, or you can think of them as really short cylinders. So we're going to use the same formula. I still recommend that you sketch the graph of the function given, so that you can just make sure that, there's nothing funny going on, such as the graph crossing over the x-axis, over the interval, or anything like that. Okay, so for this one, it's just a simple parabola, but I'll go ahead and graph it in here. We're looking at the interval from 0 to 2, so, it would just look something like this. And we definitely don't have, anything in particular we have to worry about here. We're just looking at this area, rotating it about the x-axis, and we would get a shape that looks pretty similar to this one. Okay, so our formula is, again, it always starts with a pi, and then it is the integral over the interval of the radius, which would come from the function. We're just going, straight up from the axis that we're rotating around to the curve, and that is just our function, which is, in this case, x squared plus 2, and it is squared. Dx. Pi r squared h. Keep in mind, that's why you're squaring here. That's why there's a pi. This is the volume of a cylinder, pi r squared h, or area of a circular cross section, pi r squared, times the thickness, which is dx. Okay, once again, if you would want to pause the video, try to do this by hand. I would suggest that you expand it if you need to practice this, doing this without a calculator, or go to the calculator, use Math 9. And just don't forget, okay, sometimes, like I said, I forget the squared here. Don't forget that your function is being squared and that you have to multiply your answer by pi. So for this one, I am getting 376 over 15 pi. Or in decimal form, that is approximately 78.749. Okay, so these examples, again, are what we call disk method. But take a look at the next question in your notes. How does the volume formula change if the solid is bounded by two curves? So notice here we have a curve called y1 and a curve called y2. Okay, well, you may remember from the last section that whenever we find area between two curves, we take the integral of the upper function minus the lower function, right? So we're going to apply something similar here, upper minus lower, but with volumes. This is called washer method because a cross section is no longer going to be a disk, a solid disk, but it's going to have this, circular region in the center cut out of it, just like a washer. Okay, we're not talking like a dishwasher, but like a washer like this. Okay, that's why I put the picture there. And so again, this is called washer method. And I think that this visual helps to understand why the formula is set up like this. So it looks really similar to the formula that we use for disk method, right? Pi something squared dx, pi integral something squared dx, right? But that something squared is actually the upper function squared minus the lower function squared. And that comes from the fact that you are going to have a radius from your axis of revolution up to the upper function. But then that's going to tell you the volume of this entire region, or the area. If you're just taking, the circular part, the area of this entire region. You then need to take out of it this smaller radius, do it in red, the area, I should say, of this region, which comes from pi times this smaller radius squared. Okay, so keep in mind that you have like an outer function squared minus an inner function squared for washer method when you are looking at the area being rotated being between two curves. Like this, take a look at example 2. A cup is made by rotating the area between y equals 2x squared and y equals x plus 1 with x greater than or equal to 0 around the x-axis. Find the volume of the material needed to make the cup. All right, and again, we're starting with an example where we have a really nice picture to go from. I don't know if my picture is sort of in the way, so I'm going to make that a little bit smaller, move it over. Okay, and this region that you're looking at right here would be the area between the two curves, right? But then we rotate that area about the x-axis, and what we see is this resulting cross-section. Okay, a cross-section is mainly just highlighted from the solid. Okay, So if you think about the, how to find the area of this circular region, you would say, let's find the area of the overall circle, which would come from pi times the upper function squared. And we want to take out of that the area of this hole, the region where we see a hole, and that would come from pi times the lower function squared. That radius is the lower function, and we're squaring it because of the formula pi r squared. Okay, so here's how our integral would get set up. We have the integral from 0 to 1. Notice that it does not tell you to use an upper limit of x equals 1, but that's where the curves are intersecting, and you can clearly see that on this graph. So it's the integral from 0 to 1. We need a pi in there. Of the upper function squared minus the lower function squared dx. Now again, if you were doing this by hand, you would need to expand this, simplify, combine like terms, do all of that stuff, and then do an antiderivative, okay? But since I'm trying to keep this short, I will say when you do this integral, you should get 23 over 15. Don't forget to bring along the pi, or approximately 4.817. If I were you, I would at the very least confirm that you can get those answers in your calculator. Okay, in the last couple of examples, I just want to show you that sometimes, it seems like you're given a lot of information, and when you don't have a picture, it might seem a little bit overwhelming. But as long as you sketch the graph, I think you'll find all the things that you need to set up the formula correctly. Okay, we're finding the volume of the solid of revolution formed by the region x equals 0, y equals x, and y equals x squared minus 1 squared plus 1, rotated about the x-axis. So let's take a look at these functions, y equals x, and y equals quantity x minus 1 squared plus 1. And what I want you to notice is that, there's something going on in here, and we need to zoom in on that region, especially because it says that we are also bounding by x equals 0, so we're not going to look at any region over here in these quadrants. And so I'm going to go to my window, and I think I'm going to change my x-min to -1 just so I don't completely lose my y-axis. And it didn't seem like I needed too much on this end. Yeah, let's just go to like 1, 2, 3, 4 for our x max. Okay, that looks a little bit better. I don't need to see so much of the y either, so I'm going to take that down a little bit. Let's go from -5 to 5. Okay, not bad. I think what you can kind of pick up here is that these functions have 2 points of intersection, and that does mean that we are going to have to set up 2 different integrals. Because the upper curve changes over the entire interval here. I'm going to change my window just slightly still because I want to see that region a little bit better. I think let's go to 3 on the x and -1 to 3 on the y. Okay, that looks pretty good. So I'm going to sketch that, but I'm not going to draw this part in because I don't need the curves beyond or to the left of x equals 0. Okay, So I paused the video, I sketched the graph so I could take my time, and I put a little bit of work down here that you don't necessarily need unless this was a non-calculator problem, where I set the two functions equal to each other to confirm that they do intersect at x equals 1 and x equals 2. Okay, so the tricky thing to imagine is taking these regions and revolving about the x-axis, and what would the what would the resulting three-dimensional shape look like? Okay, that's kind of hard to visualize, I know. But the good news is, as long as we are revolving about the x-axis, we can use the Washer formula. The only difference here is that we are going to have to use it twice. Okay, once for the interval from 0 to 1, where the parabola is the upper function and the line is the lower function, and then again from 1 to 2, where they change over to the line being the upper function and the parabola being the lower function. Okay, so my volume formula is going to come from pi times the integral from 0 to 1 of x minus 1 squared plus 1, that whole thing squared, that's pi r squared, minus just x squared. There's a lot of parentheses and brackets going on here, dx. Okay, that will give us our first volume. Let's call that volume 1, which would be here. Volume 2 is going to come from pi times the integral from 1 to 2 of x squared, that's the function x squared, pi r squared, minus x minus 1 squared plus 1, square that whole thing. A lot of squared going on here, I know. Okay, then once we find those two answers, we can add them together to find our total volume. Okay, the answer to the first volume is 23 over 15 pi. And the second one is 7 over 15 pi, which when added together just gives us a nice 2 pi answer. 30 over 15 pi, right? Or 2 pi. Yay. Okay, so again, this volume is just Washer method formula. Washer method formula again, just with the parabola being the upper function, which we have first here over the interval from 0 to 1, and then the line being the upper function, which you see right here in this x squared part over the interval from 1 to 2. Okay, so finally, there's one more problem that I would recommend that you try. Again, try it by graphing these two functions. Your two functions are just y equals 1 and y equals x minus 1 squared plus 1. Okay, it tells you that you are going until x equals 1 and you're rotating about the x-axis. So see if you can sketch that graph and set up the formula and find its value. Okay, and here's my graph and my formula. So because we are just looking at this region until x equals 1, okay, it's a very small region that we are revolving about the x-axis. We would, if we draw like a line in here to represent the radius of a cross section, we would get that from the x squared minus 1 plus 1 squared minus 1 squared, because 1 is the lower function, just y equals 1 is the lower function. You don't really have to write it as 1 squared, but I wanted to show that it is the upper function squared minus the lower function squared. And then finally, when you integrate, whether it be by hand or calculator, you should get 13 over 15 pi, or approximately 2.723. Okay, everybody, as usual, I hope this was helpful. Bye.